Let's talk about FP8. When running on GPUs, one of the most important factors for achieving higher throughput is to use lower precision numbers. Moving from FP64 to FP16 yields huge increases in throughputs at the loss of numerical precision. When talking about FP16, we may have formats like standard FP16 or alternative formats like BF16. The difference between these numerical formats consists of using different amounts of bits for the exponent versus the fraction or mantissa part of the number. Both of these yield the same throughput on GPUs, but they have different ways of representing the underlying numbers and different failure cases. In the recent generation of GPUs, starting with the H100, researchers have begun to explore even lower precision in the pursuit of higher throughput. This gives us formats for FP8. There are different formats that researchers have experimented with, such as E4M3, which uses 4 bits for the exponent and 3 for the mantissa, as well as E5M2. The difference between these formats is rather complicated and specific to the experiments being run in a given paper. I think we've seen researchers mostly use this E4M3 format when working with FP8. The more interesting part about this format, though, is just how careful you have to be in using it. Almost any standard operation that you do in FP8 is going to lose precision in key manners. So to make this more precise, we can actually look at the values that FP8 can actually represent. So in this table, copied from Wikipedia, we can see the actual values that FP8 is actually able to produce. Note that no other values not on this table, which is a little bit bigger than I'm showing here, can actually be represented in this format. So this is not really an integer, but it's also not really a float, as there are many values that cannot be represented, including a lot of kind of standard integer values. The main thing we're going to utilize this to do is to do very fast and very high throughput matrix multiplies. But again, we have to be extremely careful. In a recent paper, when they described how to actually do matrix multiplies, they are going to basically keep all of the main values in the BF16 format. And right before the matrix multiply itself, they're going to convert these down into FP8. But you can't even kind of sum up these values in FP8 without losing a lot of the information. So you're only going to do the multiplication in FP8, and immediately when doing the accumulation, go back to FP32, and then out to BF16 on the output itself. You can do even better by actually quantizing these values when going to the tensor core and grouping them together and scaling them to make this more numerical.